Alright, welcome everybody. So today I'm going to talk to you about organic chemistry. This chapter in IB chemistry is actually really in-depth compared to what you do for AP chemistry. And it's above and beyond what you would do for honors chemistry because we talk about specific organic reactions that we don't really cover in the regular curriculum. And when we talk about the reactions, we really go into the mechanisms. So what's happening on a mechanism level? And that's really reminiscent of what you'll see when you take organic chemistry in college. Almost the entire year is based on looking at mechanisms of reactions, and it's one of the hardest things that students find to do. So first we're going to start off with just the type of series, the homologous series. And so, that's the first thing I'm going to talk to you about. And we're going to talk about first formulas for those homologous series. So some of the objectives that you need to know for the homologous series is, what the term actually means. And in Regents chemistry, what we saw was that homologous series would refer to the alkenes, the alkenes, the alkynes. So we had the alkenes, the alkenes, the alkynes. And these were all similar because they all had the same type of general formula. If you were an alkene, you had that CN H2N plus 2. If you were an alkene, you had CnH2n. And if you were an alkyne, you were CnH2n minus 2. And I'll mention this again when I talk about this stuff, but that is, those were the homologous series that we dealt with last year. Now, they also extend homologous series to talk about things that contain functional groups. So now the alcohols are homologous series. The halides are homologous series. The organic acids, the amines, all of those are homologous series. So we'll get into that in a little bit more detail. So when we talk about organic chemistry in general, we talk about chemistry studying where carbon is the central or the main atom. And now in this case, they show you a very simple example of something like methane with CH4 with a carbon with 4 hydrogens. And most people think, if you're organic, you have to have carbon and hydrogen. There are examples where that's not true, something like CCl4. So here's a compound that's organic, carbon tetrachloride, or CTET. And that one, that is not an inorganic, that's an organic compound. But then you have something like CO2, and CO2 actually is inorganic. That one is not an organic compound. So, it's generally, when we talk about chemistry of carbon-containing compounds being organic, a lot of these compounds have properties that, can be used in organic types of reactions. And we also see that a lot of organic compounds, they're found in complex compounds that are biologically active. They're in your body. They are responsible for certain biological processes like enzymes, fats, carbohydrates, those organic molecules. They'll call it biochemistry because they're studying the effect of these chemicals on a biological organism. So here again are the different homologous series, and you've seen some of these before. So you've seen the alkenes, you've seen the alkenes. They also list, the alcohols in this case to give you an example of them. So they give you a bunch of different homologous series, but we could extend this to alkynes, we could extend this to amines, and all the different functional groups. So when I would define a homologous series, it's going to be a compound that only differs based on the number of carbons. It's going to have the same functional group. They're going to have the same general formula, and I wrote that on the first page, and they're going to have similar chemical properties. So all alcohols, they're going to have similar type of reactions. We'll see how you can oxidize alcohols, change them into aldehydes or ketones, and then further oxidize them into, if you're an aldehyde, into an organic acid. You don't have to worry about that right now. We'll get into that soon enough. And so, they're giving you 3 examples here and showing you how they only differ based on the carbon length. So the general formula is what I wrote on the first page, and I'll write that again here. We have our alkanes, which is our CnH2n plus 2. We have our alkenes, CnH2n. We have our alkynes, CnH2n minus 2. And then we have our aromatics, and those are like our benzenes, and those are CnH2n minus 6. And so these are the general formulas. We can plug in these formulas based on, the different compounds that we have and see which one fits. If I gave you something like C6H12, I could ask you, well, which homologous series does this fall into? And then you could research that and figure out, okay, well, what homologous series does this actually, fit into? Which one does it match? Another thing that we look at with homologous series are, what the boiling points are. And, depending on which homologous series you're looking at, you might see that they start at different points if they have hydrogen bonding or if they have London dispersion forces. But generally, they're going to have very similar melting points / boiling points as you look at the homologous series. And so we could see something like CH4, C2H6, C3H8, C4H10, C5H12. And we could look up the boiling points for each of these and the melting points for each of these. And what we'll see is that as we increase the number of carbons, that's going to increase the strength of the London dispersion forces, in this case London dispersion forces, because they're all nonpolar, and that's going to increase the boiling point / melting point. So this is more of a bonding type question. You look at this, you're like, well, yeah, they're bonding together. They're all nonpolar. They have these London dispersion forces, so that's what's making them have a higher melting point and boiling point. So those are, some properties about a homologous series. Melting point and boiling point, they expect you to know that. We'll also talk about, writing different kinds of formulas for these compounds. So the different kinds of formulas that you've heard of before, empirical, molecular. There's new ones here, though, like condensed structural, full structural, and skeletal. And, an example of this is something like C4H8O. And so I could try and draw this out using the octet rule and figuring this out. I have my 4 carbons. 1, 2, 3, 4. I need 8 hydrogens. So, to do this, I know personally that I'm going to need a double bonded O here in order to make this work. And I could have something like this: 1, 2, 3, 4, 5, 6, 7, 8. That'll be 8 hydrogens. So that's a structural formula. Maybe you remember this from last year, that this is known as a ketone. And we'll talk about naming these and stuff like that. But here's my ketone. It has my 4 carbons. Now let's say I wasn't sure about this and I try to draw one like this, 1, 2, 3, 4. And then I say, why don't I just put the O here at the end? Well, when I fill in the hydrogens and I put them all together, I'm going to have too many hydrogens. I'm going to have 10 hydrogens here. And so this is not going to work. Now this is my structural formula. My condensed structural formula, what it basically is doing, it's just taking this and it's just breaking it down into a condensed form. So I would have CH3, CH2, CO, CH3. And so now I have my ketone, but now it's condensed. Now something new that you may not know about is something called the skeletal formula. And the skeletal formula just would look like this. My first carbon would be here as a dot, and then I would draw a bond to my next carbon, and then I would draw a bond to the next carbon. I would have my double bonded O that I would show like that, and then I would have a line to my next. Now, when you're done with this, you get good at it. I drew in the dot at the end, but really you don't include that dot. So this dot right here would come out. And it's important to know that each end of a line here So if I were to highlight this in blue, there's a carbon here, a carbon here, a carbon here, and a carbon here. So there's 4 carbons. That's my skeletal structure. This is really how they show compounds in organic chemistry. You've seen it before when we did benzene. When I did benzene in the class a few weeks ago, talking about resonance structures, I drew benzene like this. I drew a skeletal structure for it. Each corner was a carbon. There's 6 corners, so it's 6 carbons. The double bonds are represented by 2 lines. The single bonds are represented by 1 line. So, look, I drew one of these structures here, but check it out. This is what we get. Wow. I could draw 20 of these structures. I could draw 20 different C4H8O. These are all C4H8O. Giving you the empirical formula here, which is also the molecular formula, because it represents the true molecule, is not enough. You need to draw a structure. The structure gives you so much more information. I could even take this and I could make it into a skeletal formula. So here's just comparing all of these things, and on the next page I show you all the skeletal formulas. But here's C4H8O, and the empirical formula in this case, the molecular formula, is the same. But now they could have different structures. Here's structure 1 from the previous page. Here's structure 8 from the previous page. I could show it condensed. I could show it condensed in either case, or I could show it as a skeletal formula. You should be familiar with all of these representations and know how to draw them in all of these different representations. That's really, really important. All right, so you could practice this. Try 5 different ones of these. Don't look back at the previous page. Try 5 different structural formulas of C4H8O. See what you come up with. Make sure that you can draw those. These have a word. They're called isomers. We'll talk more about isomers in the next presentation, but that's what they're called. So look, here's some key points to this. You have carbon in the compounds. That's what makes it organic. You don't need hydrogen, but it's there a lot. Not every compound with carbon is organic. When you have a homologous series, they differ only by the number of carbons in their chain. They'll have the same functional group if they have a functional group. They'll have the same general formula. When you have a melting point and a boiling point, it's going to increase as you add on carbons. You get those stronger LDFs, and in some cases, hydrogen bonding, depending on what the molecule is, or London dispersion forces and dipole-dipole. And then, when you want to show something as unambiguous as possible, use a structural formula. Don't use an empirical molecular formula. It doesn't give you enough information. All right, thanks for watching, and next time we're going to do some isomers. All right, thanks so much. Have a great day.